Okay, everyone, welcome back to session 2 of day 5. Samik will continue with the second part. Over to you.
Okay, so let me begin. So the title of this lecture is Stable Homotopy Theory. And so remember from last time I introduced some aspect of homotopy theory, the basic constructions and so on, co-fiber sequences, fiber sequences. Those are the important things. But before I start out this lecture, let me just say that the kind of thing I'm planning to do in these lectures. So, so you know statements like these, like Poincaré duality. Poincaré duality. It says that um, if M is a closed oriented manifold, if M is a closed oriented manifold of dimension n, so I will put an n before manifold, so n manifold, then we have then Poincaré duality tells us that the kth homology of M is isomorphic to the n minus kth cohomology of M. And from Poincaré duality on this, so Poincaré duality, there are many versions, there are number of statements. Mm, and one thing you deduce, so um, if you look at a first course in algebraic topology, you would perhaps do this theorem, and you would also perhaps do this thing which comes up as a corollary, uh, Alexander duality. Um, so this says that if X is a closed subset of Sn, X is a closed subset of the n sphere, then the kth um, reduced kth homology of Sn minus X is isomorphic to the reduced n minus k minus 1 of X. So it's so the cohomology of X appears as the homology of the complement of X in Sn. So my the purpose of my lectures is, my objective is to view these theorems from view these as a theorem in stable homotopy theory. Rather, what I would like to say is that these theorems are part of more general results about uh, something we will call dual objects in stable homotopy theory. So that is my objective. So so today, so today I will talk about stable homotopy theory, and in my lectures next week I will come back and talk about what I mean by this dual objects and what is the theorem I am talking about. So one of them is going to correspond to something called Spanier Whitehead duality, and the other one is going to correspond to Atiyah duality. Okay, so today I want to talk about stable homotopy theory, and let me get to the point here. All right. So the So last time, remember, we defined homotopy groups. We defined homotopy groups. Defined homotopy groups, and we talked about how to um, we talked about the category uh, obtained by inverting weak equivalences in topological spaces, basically. But I didn't say very much about computations with homotopy groups. Uh, the reason is that the computations are very hard, and while we know that if I have a uh, fibration that induces a long exact sequence in homotopy groups, but that does not really calculate homotopy groups for us in a lot of examples. So the things with that we know, like even for spheres, I know that S1, um, I know that the fundamental groups of S1 are given by z if k is equal to 1 and 0 if k is bigger than equal to 2. And the reason is that S1 has a universal cover R. R to S1 is a covering space, and we have seen that I have commented before that if I have a covering space, then the homotopy groups in dimension greater than equal to 2 isomorphic, and the real line R is contractible. So yeah, so the real line is contractible, and so we have that pi k of S1 is 0 if k is bigger than equal to 2. Okay. Now for S2, you have this fibration called a Hopf fibration. So I identify S2 with CP1, and then you know that there is a action of the circle on S3 uh, whose quotient is whose orbit space is S2. So you have this fibration S1 to S3 to S2. So this implies that, and so this map here is the Hopf map eta. So eta is the Hopf map. Okay. So that tells you that pi k of S2 is isomorphic to pi k of S3 if k is bigger than equal to 3, and pi 2 of S3 is of course 0, and pi 2 of S2 is isomorphic to Z. All right. Uh, so you have that, but this again shows that if you have a if you want to calculate homotopy groups of spheres, having these kind of fibrations with both base and fiber and the total space being spheres is very helpful. So that's another thing um, which is helpful. But again, uh, the Hopf invariant one theorem says that this does not occur in a large number of examples. Okay, so so you can calculate like this, but you will if you go to the literature, you find that the calculations are not as extensive as we have for homology groups, and the reason is that um, when you have homology groups, homology uh, satisfies, like, one of the axioms of homology is excision, but homotopy groups does not have this property. So one of the consequences of excision is the suspension isomorphism. excision is more general than this, but let's recall this. So the suspension isomorphism says that if I look at if X is a base space, then H k plus 1 of the suspension of X reduced is isomorphic to the reduced homology of X with any coefficients. But it is not true, not true that pi k plus 1 of suspension of X is isomorphic to pi k of X. Rather, what is true is that, I mean, it's not true, but there are some partial results. So so remember, uh, we define X is said to be k connected if pi I of X is 0 for all I less than equal to k. So if I take Sn, that is n minus 1 connected. And then there is this theorem, Freudenthal suspension theorem, suspension theorem. So so if X is k minus 1 connected, then I look at this suspension homomorphism from pi k of, oh sorry, not pi k, rather pi r of X to pi r plus 1 of the suspension of X. So pi r of X is, remember, the homotopy class of maps from S to SR to X. And now you take a map and map it to the suspension. So you get a map from SR plus 1 to the suspension of X. So that's the suspension homomorphism, sigma, or often it is also denoted by E. So if so under this condition that X is k minus 1 connected, then this is um, isomorphism if um, R is less than equal to 2k minus 2, and this is surjective if R is 2k minus 1. Okay, so if it is k minus 1 connected, it is isomorphism until 2k minus 2, and it's surjective if R is equal to 2k minus 1. So the thing here, the point here is that uh, depending on the connectivity, you get a range of dimensions here where this suspension isomorphism holds. It does not hold if it is true for all R, but it holds if you go up to roughly twice the connectivity. So there is still a non-trivial range from k to 2k minus 2 where this suspension isomorphism holds. But so the analogy is not just with the suspension isomorphism. If you look at the statement of excision, there is a statement about homotopy groups also, which mirrors the statement for excision for homology, and that is called the Blaker's-Massey theorem. I will not write that. I don't want to enter into a discussion on in that, so I will not write that. But this Freudenthal suspension theorem is a special case of that. This what this tells me is that if I if I just look at this range, if I try to isolate this range where you have this suspension being an isomorphism, I would it would it would be like it would behave like homology, and that is the case. So uh, you take the clue from here and you define stable homotopy groups. So stable homotopy groups of spaces. So stable homotopy groups. So you define pi k s of x. This is the direct limit over n pi k plus n of sigma n x. So what is the direct limit taken over? So if you have a map from sk plus n to sigma nx, then you can take the suspension and that will give you a map from sk plus n plus 1 to sigma n plus 1 x. And so you pass to homotopy classes and then you get a then you can take the direct limit which becomes an abelian group, and so this is defined for all k bigger than equal to 0. Actually it even makes sense if k is less than 0, but in this case if x is a space it's going to be just 0 if k is less than 0. So this is defined for k bigger than equal to 0, and if you apply this Freudenthal suspension theorem, you see that this Freudenthal suspension theorem, this implies that the value that the Freudenthal suspension theorem implies that after a point this will just give isomorphisms. So the value of this stable homotopy group is it in some initial phases it will change. These pi k plus n sigma n x will change, but after for every k there will be an n after which this will be constant. So so this Freudenthal suspension theorem is that this the maps in the maps in in the direct limit system are isomorphism after some n, are isos after a finite stage, finite stage. Okay. So if you want to think about so now if you now this pi k s of x even makes sense if x is s naught, right? Because if you so k equal to 0, this corresponds to pi n of Sn for n large, and that is actually z. So this is z by the Hopf degree theorem, and k equal to 1, this corresponds to pi n plus 1 of Sn, n large, and this actually turns out to be z mod 2, and this is generated by suspensions of eta sigma n minus 2 of eta. Okay, the Hopf map which I told you about, it's a map from S3 to S2. You suspend that n minus 2 times, that will give you a map from Sn plus 1 to Sn, and also the twice the map is 0, all that one can verify and show that this is the case. And so it turns out that these stable homotopy groups, there are systematic ways of calculating them, and it's better, it's easier to calculate than than the usual homotopy groups. It's slightly easier because there are systematic methods, and these methods are I mean the most important facts we will state later on, which is the structure of this the structure structure of stable homotopy theory, which I will come to in a bit. Okay, so let me go to the next page. Okay, so you can also analogously define stable homotopy classes of maps. Stable homotopy classes of maps between spaces. You can define it like this. We use this curly brackets to denote the stable homotopy classes, and this is direct limit over n, sigma n x, sigma n y, and all are pointed, so I should put a star there. So those are the stable homotopy classes, and so if I put sk instead of x there, I get the kth stable homotopy group. All right, and so and then there is this Spanier Whitehead category. This is SW. These objects are so the point is, before writing down the next word, let me say this, that the point is we want to define. So we have these stable homotopy classes of maps, and it clearly has some importance, and we want to form this category, who we want to form some kind of a homotopy theory, and the homotopy classes of maps should be these stable homotopy classes of maps. And so the so first firstly one or even before these ideas of homotopy theory was there, people wanted to understand uh, what is the something about the stable homotopy theory, in the sense that you should be able to do all the homotopical constructions which we described last time, like taking co-fiber and so on, and the homotopy classes should be the stable homotopy classes of maps. So it should contain the spaces. You should be able to do all the constructions like the co-fiber sequences and so on, and uh, the homotopy classes should be the stable homotopy classes of maps. So the first attempt at achieving that is the Spanier Whitehead category. So the objects are CW complexes, and morphisms, maps in SW, and morphisms are these stable homotopy classes of maps. But you see, if I do this, then I don't have the construction of a co-fiber. Let's do this example, which I thought was uh, it helped me understand why we need to do what we are doing later on. Okay, so you see, you take the Hoff map from S3 to S2. Now I can view this as a map from S3 to S2, but this is also I can also view it as an element from S1 to S0, because uh, you are just taking as direct limit of sigma n x, sigma n y. So this eta actually belongs to sigma 2, is a map from sigma 2 s1 to sigma 2 s0. So this thing is definitely an element of the homotopy class of the stable homotopy class of maps from S1 to S0. So that is valid. But now if I do this, if eta belongs to here, then you would ask, what is cone of eta? What is the mapping cone of eta? Well, uh, surely the second suspension of eta is this eta. So I should write this as this eta. I will just write it as sigma 2 of eta, And if I take the cone on that, uh, such this both of these are homotopy co-limits, so I will commute them past each other. So this is sigma 2 of cone of eta. And what is the cofiber of the Hoff map? That is nothing but CP2. Okay, so the problem here is that I don't have an object in my category whose double suspension is CP2. So this cone of eta does not exist in SW, not exist in SW. Okay, so I hope you understand this point. So this tells me it's a pretty. I mean, if you view examples like this, you will see that there are whenever we hit a map which is not a suspension. I mean, whenever we hit a map between say two suspensions, which cannot be realized as a suspension, you will end up with something like this. So that means that I need to put a lot of objects which are going to be sigma inverse of something. Okay. So to take care of such constructions, we need to actually homotopically invert the suspension functor. That's the that's the thing that's the thing which we can conclude from an example like this. So so this Spanier Whitehead category, although it has these homotopy classes of maps, it does not capture the stable homotopy category because we cannot do homotopical constructions. So to um, so we need to construct a category which has the topological spaces and the suspension functor is homotopically inverted, and for that we define spectra. Definition: a spectrum X is a sequence of based spaces always xn together with structure maps from sigma xn to xn plus 1, and maps between maps between spectra a map from x to y is a sequence of maps xn to yn which commutes with the structure maps, which commutes with the structure maps. Okay, so a spectrum is a sequence of spaces xn plus structure maps from sigma xn to xn plus 1, and a map between spectra is a sequence of maps map between spectra x and y is a sequence of maps from xn to yn which commutes with the structure maps. Okay, uh, hmm, right. Uh, Now, well, this is a definition. So later we will define what are homotopy classes of maps between spectra. You see, now you know what a model category is, so you know that you may try to define a category in a certain way, but to get to the correct homotopy classes of maps, you need to take special objects to evaluate them in. So like topological spaces, you cannot take just homotopy classes of maps for any objects. You need to take CW approximation and then take the homotopy classes of maps between the CW approximations. So similar, so something you have to do here. So we will wait a little bit for before defining the homotopy classes of maps. Uh, so so later on we will define the homotopy classes of maps. Okay, so this will be defined later. So it's not so one naive way of doing it is you just look at these maps. Clearly, these maps have the structure of a topological space. You can just look at the mapping space. You just so it's a subset of all maps from xn to yn which commute with the structure. So you just put that topology and you can take pi 0. But unfortunately, that is not going to recover the right um, homotopy classes of maps unless x and y are nice. Okay, so we just postpone this for a little bit. We will define it later in the talk. But how do spaces yield spectra? This is the by via the suspension spectrum. So if x is a space, then you can define this sigma infinity of x um, by this is the suspension spectrum of x, suspension spectrum of x. So that's defined by sigma infinity of x n equal to sigma nx, and the structure maps are just the identity. Structure maps are identity. You see, sigma of sigma n is sigma n plus 1. Um, okay, so this gives you the so the so this gives you a functor from the category of base topological spaces to the category of spectra. It gives you a functor sigma infinity, and this functor has a right adjoint omega infinity, which sends a spectrum y to the 0th space. Okay, so this sigma infinity and omega infinity, sigma infinity is left adjoint to omega infinity. It is left adjoint to omega infinity. All right, so that is very easy to check. Next page. So now homotopy groups definition. Homotopy groups. Homotopy groups. So if x is a spectrum, you define pi n of pi k of x is defined to be the direct limit over n pi k plus n of xn. You see, this is almost so in the case of the suspension spectrum, this is exactly the definition of stable homotopy groups. And it's I'll leave it to you to figure out the maps in the direct limit. It's exactly the same way. You have to do the suspension and then you have to apply the structure map. But one thing to notice here is that are defined for all integers, are defined for all uh, k in Z. So if k is negative, you have to this direct limit just starts from minus k, and so these are defined for all integers. Uh, and if you take pi k of sigma infinity of x, this is just isomorphic to the kth stable homotopy group of x, and this These are 0 if k is negative. These are 0 if k is negative. Okay, and we define a weak equivalence of spectra. Equivalence of spectra is a map which induces isomorphisms on all pi k. Is a map which induces an isomorphism on all pi k. On all pi k. So examples. One example is this suspension spectra, but there are other examples also which I should mention. Is Eilenberg-MacLean spectra. In spectra. So I did not talk about Eilenberg-MacLean spaces last time, but there are these spaces KAN. These are for A is an abelian group. A is an abelian group. KAN satisfies pi r of KAN is 0 if r is not equal to n, and it is a if r is equal to n. All right. So now you see that you will observe that KAN is equivalent to the loop space of KAN plus 1, and by the suspension loop adjunction, this induces a map from the suspension of KAN to KAN plus 1. So this allows us to define a spectrum HA such that HAN is KAN, and the homotopy groups you will easily calculate of HA is A if k is equal to 0 and 0 if k is not equal to 0. So these are Eilenberg-MacLean spectra. Their homotopy groups are all concentrated in degree 0, and it is 0 outside 0. And so there is a separate story which I will not go into here, is that starting from a generalized cohomology theory, you can construct a spectrum uh, because there is a theorem called the Brown representability theorem, which says that if you have a generalized cohomology theory E, that means I have for every CW complex I have I can define En of x, where n is an integer uh, which satisfies the long exact sequence and Beige axiom and homotopy invariance. So there is a Brown representability theorem which says that those functors E upper n of x are representable by spaces E lower n, and some from basic categorical properties one can deduce that the E lower n will be the base loop space of En plus 1, and so they will give you spectra, but I will not go into that in this talk. So let me just try to show in the remaining time. I think I started a bit late, so I have 15 minutes. In the remaining time, I should tell you why this is a suitable category for the properties that we advertised, and in the end I will say that we wanted more properties which this did not have, and I will make a comment about that. Okay, so why is this a suitable category? So one of the properties which we advertise is that suspension should be homotopically invertible. So if I have a spectrum, if X is a spectrum, there are many homotopically equivalent ways of defining suspension. One of them is this. So I define suspension X by sigma X n is suspension of Xn. So in each level I am just taking the suspension, and the structure maps are obvious in this case. I am just taking the suspension of the structure maps. Okay, so that is sigma, and of course there is a many homotopically equivalent ways of defining sigma inverse, but I will choose one, namely sigma inverse x, defined as sigma inverse x at n is x n minus 1. So that means, and I have to define what happens at 0. So that is just a point. So if x starts from x0, x1, x2 and so on, then sigma inverse x will start, will push everything one step to the right. Okay. So now you see that if I define it like this sigma inverse is the same functor as sigma inverse sigma, but I also have a map from sigma inverse x to x, uh, which at level n, at stage n, sigma inverse x will just give you sigma of xn minus 1, and here at level n it's xn, and this you just this is the structure map, and you can check that this is a weak equivalence. This is a weak equivalence. So in the homotopic category, they will give you the same object. So in other words, the this suspension functor is homotopically inverted. All right. Uh, so this suspension functor is homotopically inverted. So the next point is mapping cones, but so the mapping cones. So these you can do it level wise, so defined level wise. So if you have a map from x to y, then the mapping cone is just you take the mapping cone at each level. So a map from x to y is a map from xn to yn commuting with the structure maps. So if you take the mapping cone at each level, that gives you a spectrum. Another definition: X is said to be an omega spectrum to be an omega spectrum. X is said to be an omega spectrum if the adjoint of the structure maps, if the adjoint of the structure maps, so the adjoint of the structure maps go from xn to omega xn plus 1 if these are weak equivalences of spaces. All right. So you see one of the examples is the Eilenberg-MacLean spectrum. Now any spectrum which is defined from a generalized cohomology theory, by which I said verbally, they will be examples of this. More explicitly, you can define, you have Bott periodicity, which says that if you take the space Z cross BU, then the double loop space of this is same as Z cross BU. This is from Bott periodicity. Okay, and then so you can define a, so if you have this spectrum which starts from Z cross BU, and then you have loops of Z cross BU, and then again Z cross BU like this. This defines a spectrum because every the 2nth space is the loops on the 2n plus 1th space, and the 2n plus 1th space is the loops on the 2n space, and so on. So this gives you a spectrum which is called K. This gives you a spectrum which I write as Ku, and this is the this represents a cohomology theory, namely complex K theory. So this is the complex K theory spectrum. Similarly, you have a similar construction for real K theory. Okay. Next thing is homotopy classes of maps. So remember, we have already defined a space of maps. So if x, y are spectra, we have defined a mapping space, maps from x to y. This is a space. Okay. Now, if y is an omega spectrum, then you can define, we define this. This is the homotopy classes of maps between spectra as the pi 0 of this mapping space. Okay, and this so, and then I should state a theorem. This theorem says that for every spectrum x, for every spectrum x, there exists omega spectrum Lx to plus map from of spectra from x to Lx, which is a weak equivalence. So in this rudimentary sense, if you want to calculate homotopy classes of maps between spectra, then you just replace the right hand side, replace the target with an omega spectrum, and then you can just calculate the homotopy classes as the normal homotopy classes of maps between the two spectra. Okay, but there is a bigger story to all this. If you do it from the point of view of model categories, then you can define fibrations, cofibrations, and the homotopy classes of maps are just the usual homotopy classes between fibrant cofibrant objects. And it turns out that on the basic level, this is the kind of thing which you are doing. You have to replace the target with a fibrant one, which is an omega spectrum in the usual model category structure. But I don't want to talk about the model category structure here because I still have a couple of things to say before I stop. So that's one thing that defines homotopy class of maps. The next thing is cofiber sequences, and this is a rather important point, and it came up in Shrikant's lecture as well. That so the cofiber sequence, remember, looks like this. Now we are in spectra. Okay, x to y to, so if this is f, the next one is the mapping cone of f to the suspension x, and so on. Okay, and we have seen that in spaces if I apply homotopy classes of maps into W, this gives this gives uh, this gives actually a long exact sequence of pointed sets when you are looking at spaces. Now there are two things happening when you are in spectra. First is that because the suspension is invertible, that means every spectrum up to homotopy is a double suspension. So these are always abelian groups. Okay, so that's part of the triangulated structure which I am talking about here. So these are always abelian groups. So this gives long exact sequences by exactly what we have proved last lecture for spaces. But the thing is that which did not happen for spaces is that if I apply this functor, uh, they also give long exact sequences. That's a simple check with the fact that the suspension is invertible, and I will leave it as an exercise. In fact, Srikanth has already mentioned this in his in some form in his lecture, so I will uh, I will not even elaborate on that. But this is a this last point here is that W, I mean the this W comma dash in gives you long exact sequences. This did not happen for spaces. That's a important point to remember. So this tells you that if I take the stable um, this the stable homotopy groups, this gives you a homology theory. Okay, so that has long exact sequences. It has excision, and it has a wedge axiom and so on. Okay, it that's not true for usual homotopy groups. Okay, couple of things. I think I have out of my 50 minutes, but Anant, I think it's okay to take 5 minutes, too, right?
Sir, Anand sir is left, I think.
Uh,
He's not joined.
hmm?
Just go ahead,
Okay.
Samik.
Yeah. Okay. I'll finish quickly in 5 minutes. So there are a couple of things which I should talk about. So whatever I said, just doing uh, this. So I define this category with these homotopy class of maps, and uh, it's uh, it's sufficient for some respects, but it's insufficient for a couple of things, and that's the last thing which I will say. What you want is that um, to do homotopy theory, you also need something called the smash product of spectra. So if I have spectra x and y, I need to define a smash product uh, which which should generalize the smash product of spaces, right? So you can do the smash product of spaces. You take the if you take sigma n of the smash product, uh, that's uh, that's again sigma n x smash sigma m y is sigma n plus m of x plus x smash y. So this smash product, if I put it in level n, this should somehow be related to the wedge uh, over k between 0 and n xk smash yn minus k. So it has to be do with this. So, but if I try to define it like this, there is a problem, because if I try to define the structure maps for this, I can take the suspension, but now on the right hand side, I can either put the suspension on the x and take the structure map for x, or I could put it on y and take the structure maps on y, and and there is no good bookkeeping which does all that together. So there is a problem. to the problem is defining structure maps. Structure maps. So what I really get is like a bi-index spectrum. I mean, you could, which you could, like, you should have structure maps in two directions, but from there to get the structure maps in one direction is a problem. Um, Another thing is you want to define a function spectrum uh, which covers the analog of the mapping spaces. So you need a function spec. You want to define a function spectrum which so for XY spectra, you can take f of x, y. The nth space would be something like maps of spectra from x to sigma minus n of y. Okay, uh, so for this, this will also run into a similar problem. What is a similar problem? So if you want to define the structure maps, whether to use the structure maps of y or to use the structure maps of x. So this is a problem, and unfortunately, the category which I described is not good enough to handle this problem. So so one has to look at other points of view, and this was an unresolved issue for many years in homotopy theory, that uh, to find to find a good category of spectra, which is so find a good model category of spectra which has these symmetric monoidal structures, that the smash product and also the mapping space, which mapping spectrum which matches these homotopical mapping spectrum. So I'll just write it as a theorem. Now this has been in the 90s. This was discovered. There are two different models. I'll just write it as a theorem. Uh, there is a category equivalent equivalent to the category of spectra which is closed symmetric monoidal. So symmetric monoidal means that I have a smash product, and closed means that I have a mapping spectrum which has the usual adjunction properties. Is closed symmetric monoidal, recovering the homotopical smash product and function spectrum described with a function spectrum we just talked about, described here. Okay, so the unit object is S, which is the suspension spectrum of S naught. Okay, so I have this symmetric monoidal means that I have that's the smash product, and closed means that I have these function spectrum. Okay, so for this I would there are two different categories which does this. One is the category of symmetric spectra or variants. Uh, Symmetric spectra or orthogonal spectra, and another is a construction using operands, which I don't want to elaborate at all. operads. So for the idea behind symmetric spectra or orthogonal spectra is that you define these xn, instead of taking them to be base spaces, you take them to have a structure of the symmetric group, and using those the structure of the symmetric group, you can do the uh, you can use the symmetry group to do the bookkeeping which is required to define the structure maps in the smash product. That's all I want to I will say. But but it has been done, and the symmetric spectra, uh, they are they are reasonably nice to understand and to compute with. Okay, so I am really out of time, so I will stop here, uh, and so let me just stop. So I think I should stop sharing the screen. Stop.
So are there any questions for Shamik?
I have a question.
Yeah, go ahead.
Yeah, this is concerning that example. Can you please, Shamik, can you share the
Yeah, 1 second. Which example?
the one where you motivated spectra by looking at the Hoff map and suspending it? And
Screen. Start. One where I'm using the Hoff map. This one. No, before.
before this.
Yeah,
Now,
this one, right?
yeah. I didn't understand. Can you explain towards the end what was the problem?
Yeah. So if you think of this eta as a map from S1 to S0.
Mhm.
So now if I take the cone, if the mapping cone existed in the category SW, then you realize that the double suspension of that is CP2, because double suspension is the Hoff map from S3 to S2, and the mapping cone of that is CP2. I mean that so CP2 is obtained by attaching a force cell to S2 along the Hoff map. So it is the mapping cone of the Hoff map. So if it should have this property that double suspension of C eta must be CP2, but in SW the objects are all CW complexes. So I should have a CW complex whose double suspension is CP2, which is not possible. So that means that this mapping cone of eta does not exist in the Spanier Whitehead category.
Towards the end, yeah, another question.
Okay, different one.
Towards the end, you talked about the theorem, right? The final.
Yeah. Okay. Yeah.
So you said that you're talking about. So basically, we wanted to enrich spectra. I mean, in spectra, and we wanted a symmetric monoid, basically Cartesian closure, something like that. We wanted some Hom tensor rejection type of thing. Right?
Yeah.
So how was that problem fixed? As I mean, because as you said, there are some issues, right? So
yeah. So the thing is, you have to say, for example, in symmetric spectra, what happens is the objects are, I mean, they are sequences of spaces, but each xn has an action of the symmetric group. Okay. So you see that. So when you So in the symmetric spectrum, what happens is you can take this. So if you take xk dash yn minus k, that has an action now of sigma k cross sigma n minus k. So now you have to induce this space up to sigma n, and you take the you take if you take now the wedge of all of these, so that you can there is a way uh, putting the structure maps in a proper way in that sense. I don't want to write down the definition here because I am not prepared. I think I will make a mistake. But you can there are many good references on symmetric spectra. So the original thing is a paper by Harvey, Shipley and Smith. It's called symmetric spectra. You can look at that.
But just as a question, like, how does it connect to the original one? Because the original spectra doesn't have any symmetric group action.
No. So the way to view it is that whatever I have described is the kind of what happens in the homotopy category. Okay, so I shouldn't really say this Quillen equivalent to the category of spectra because I have mentioned model categories, but I haven't really said anything about the model category structure. So what I have described is basically what should happen in the homotopy category, and then uh, so then there is a theorem which says that it recovers the homotopy this construction. So actually this entire program, this has a long history. So the first so the homotopy category which I tried to kind of talk about, this is there in Adams's book on stable homotopy and generalized homology, and he does try to make sense of the smash product, but if you look at it, it's a very long section, and understanding that completely is a very difficult thing. So later on, people made various other constructions. So one of the constructions was by Louis May and Steinberger, and that so that there the objects were actually not just omega spectra, a very special kind of omega spectra, and there they constructed this smash product, uh, not exactly in the category but somehow up to a contractible space of choices. Okay, so after Louis May and Steinberger, people had a reasonable idea about what the smash product should be. I mean, people had a reasonable idea earlier also, but people had a more concrete idea, I should say. And then the exercise was when all these models like symmetric spectra and orthogonal spectra came about. The exercise was to show that uh, as a model category it is equivalent, and the derived smash product is actually the smash product which is described up to a contractible space of choices in Louis May and Steinberger's book. So so there is a big story behind all that, but once we have all that, we can work in the stable homotopy category, thinking that there is actually a model which has this closed symmetric monoidal structure, and that's all I would use for my later lecture. So that's why I just wrote the theorems separately.